Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this homework problem, you are given the specific rotation of a pure enantiomer, S plus 2-butanol. The S refers to the structural chirality. The plus refers to how plane polarized light is rotated. It's given plus in brackets because the plus 13.52 means a rotation to the right. The question you're asked is, what is the mole percent composition of the two enantiomers if the specific rotation of the mixture is alpha mixture plus 5.408 degrees? In order to find the mole percent composition, we must first determine the optical purity. In a mixture of enantiomers, optical purity is defined as the ratio of the specific rotation of the mixture. Okay, so the specific rotation of the mixture, I'll just put mixed, divided by the specific rotation of the pure times 100%. Well, if I plug in the numbers and solve, I get plus 5.408 degrees. Now, which specific rotation of the pure do I put in? I mean, do I put plus 13.52 or do I use the other enantiomer, minus 13.52? Well, what tells me which one to use is actually the rotation that's reported for the mixture. If the mixture is rotated to the right, positive, I use the plus 13.52. But if the rotation was to the left, minus, I would use minus 13.52. So here I put plus 13.52 degrees. And if I multiply that by 100%, 5.408 divided by 13.52, if you punch that into your calculator, you will find that it equals 0.40. And if you take 0.40 times 100%, you will get a value of 40%. Optical purity is 40%. What does that mean? That means 40% of the sample is rotating light. That's what optical purity is. And since it's rotating light, that 40% is S2-butanol. But you can't report the mole percentage as 40%. It's not. Because if 40% rotates light, what's the other 60% doing? Well, the other 60% doesn't rotate light. Does not rotate the plane polarized light. Why not? Because it's a racemic mixture. The 60% is actually 30% S and 30% R. It's a racemic mixture. And so if I take this 30% S plus the 40% S, those two values give me a mole percent composition of 70% S2-butanol. And 30% R2-butanol. And I should really say S plus 2-butanol and R minus 2-butanol. Always remember, when you have an optical purity problem or a question asking mole percent composition, first solve the optical purity. And note that the percentage you get in the optical purity is not the mole percent composition. You must subtract that from 100% and find out how much is the racemic mixture. And then add the appropriate components together to get the 70% S2-butanol. Okay, now the next question you had to do for homework was an interesting problem that required you to show how you could establish that S2-butanol, the S plus 2-butanol, really had an optical rotation to the right. The S plus 2-butanol really had an optical rotation of plus 13.52 degrees, and not a rotation to the left. You had to show it does not equal minus 346.48 degrees. Now, the reason you're asked this question is if I draw a very large circle here, and I measure from this position, a rotation, I'm going to exaggerate. Let's assume this position is 13.52 degrees. Here is a rotation to the right of 13.52 degrees. Well, a left-hand rotation of minus 346 would take you to the exact same position. Because they are exactly the same position, how can you tell whether the rotation's to the right, 13.52 degrees, as opposed to the left, minus 346? Now, in class, we explained that you could do this by calculating an observed value, by using a cell, for example, double the path length. If you use double the path length at 1 gram per mil concentration, the observed rotation would be 2 times the 13.52. It would be 27 degrees, if that was the real rotation. If it was to the left, minus 346, then you'd get double minus 346, which is what, 680, 692 something? And the position of 692 degrees is not the same position as 26. Okay. Now, this is what we covered in class. The question here was, how could you use a mixture of enantiomers to show that the specific rotation is really plus 13.52 and not minus 346? In order to answer this question, all you have to do is pick any old arbitrary mixture. Okay? So what I'm going to do is say, and we'll draw a circle again after this. Let's assume we have a 35% mixture. 35% R with 65% S. If we assume we had this kind of mixture, then 35% R would combine with 35% S to give us a racemic mixture, a racemate. That means 70% of the sample would not rotate light. If 35% of the S was used up with 35% of the R, that would leave only leaving 30% of the S to rotate light. And that 30%, therefore, is my 30% equals the optical purity, what we call optical purity. Now I can use this value of 30% and put it equal and solve for the specific rotation of what we'd see for the mixture. What do you mean? Well, I can say 30% equals the specific rotation of the mixture divided by the specific rotation of the pure, and I'm going to check out both pures. What if it was 13.52? Well, if I do that for 13.52 times 100%, and I solve for the specific rotation of the mixture, I will get a value of 4.056 degrees. Now, if I do the same equation and solve for a specific rotation of the mixture, but this time I plug in the other possible value for the specific rotation times 100%. If I solve the specific rotation of the mixture from this equation, and solve this equation, I should get minus 103.94 degrees. Now let's compare these two values on our circle. So I'll make some room up here. Draw a large circle if I can. Okay. So what would I see experimentally? Could I distinguish between these two? And the answer is, if I did the experiment and I was watching for the rotation. Okay, so let's say here's the starting position. Well, a rotation to the right of 4 degrees would be really, really tiny. Okay, it would be a really small rotation to the right. So that would be approximately a 4-degree rotation. A rotation of minus 100 would be a little more than 90, about 10 more degrees than 90. So it would put it about here to the left. It would rotate to this position. And that would be roughly minus 103. And the interesting thing is this position and that position are different positions on the circle. They can be distinguished. So if you took a 35-65% mixture and you simply ran a polarimeter on it and looked to see if the rotation reduced to 4 degrees or reduced to minus 103, that would tell you which of these two values was the correct value for 2-butanol. If the observed rotation of the mixture was 4 degrees, you know it is plus 13.52. If the specific rotation of the mixture you observe is minus 103, then you'd know it's minus 346 to the left. Okay. So, using a mixture can be used to help discern which rotation is correct. And so, to answer this question properly, I would write a short paragraph after this, showing the arc, showing that minus 1,3 leads to a different position in the circle than the 4, And because of this, if you carried out polarimetry, you would just look to see if this mixture rotated 4 degrees or minus 103. If it rotated 4 degrees, then the 13.52 is correct. If it rotated 103, then the minus 346 would be correct. So you can use optical purity to help discern, in mixtures, help discern whether the rotation you're observing is actually to the right plus 13.52 or to the left minus 346.48, which in a circle brings you to the same position. In this case, it actually turns out to be plus 13.52 degrees. Okay, well that's it. I'm Dr. Brian Lloyd. This is my Scribblecast for Homework Solutions. Thank you very much.